rarer mediums comes first and then the denser medium comes first. When that is the case, you will have rarer medium as N1 and denser medium as N2. The part of the sphere which is actually available for the fall of incident light on the surface is said to be aperture. Where the incident ray is emerging, that space is called as object space, and where exactly the refracted ray goes and hits, that space is called as image space. Hello everyone, I am Rinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to session 4 of chapter 9, and chapter name is Ray Optics and Optical Instruments. In today's chapter, that is in today's session, we are talking about something more about the equations which relates the critical angle as well as the refractive index. And we learn about the applications of total internal reflection, on which the topic we had discussed in the previous session, that is session 3. And finally, we will have something more about the spherical surfaces and the refraction in case of the spherical surface. So the first topic will be like relation between critical angle and refractive index. So you all know, so there is a surface which is present over here and there is an object which is present at the end, that is denser medium, and you have a rarer medium. Remember, whenever an incident light is incident from one direction and that area is considered to be the refractive index, will be the first refractive index. So suppose that is the incident light is traveling from denser to rarer. So where exactly the incident light lies? It's in the denser medium. That is why the refractive index is called as N1 and rarer medium will be N2 because it's a second medium for which we will be traveling, correct? From first to the second medium. So if suppose it is ulta, that is opposite of it, rarer mediums comes first and then the denser medium comes first. When that is the case, you will have rarer medium as N1 and denser medium as N2. So that is the minimum thing what you have to know. So here there is a normal which is drawn over here to the object. From this place, it makes an angle which is said to be equal to a critical angle. So incidence is equal to critical angle I. So how exactly is the refracted ray? It lies on the surface. So this makes an angle with the normal and that is nothing but 90 degree. So when we have this image, consider a ray traveling from denser medium to a rarer medium which has got the angle of incidence to be equal to the critical angle. And if it is equal to the critical angle, the refraction, that is the angle of refraction is said to be right angle, that is at 90 degree. If this is the diagram, whatever I told you right now will be the description under it. Under that you will have to write considering Snell's law, that is from Snell's law. What is that you had? N1 sin I is equal to N2 sin R. Because in case of second refractive index, you are having angle of refraction. First refractive index, you have angle of incidence. So, according to Snell's law, sin I by sin R is nothing but N2 by N1. So, what is sin I? We know that I is equal to C and R is equal to 90 degree. Okay. So, if this is Snell's law format, we will apply the same thing for the above equation. Call it as equation 1. And how do you do that? N1 into sin C is equal to N2 into sin R, that is 90 degree. Sin 90 degree is said to be 1. So what remains is N1 sin C is equal to N2. Retain your sin C at one side. You have sin C is equal to N2 divided by N1. So what will be your C? C is equal to sin inverse of N2 divided by N1. So this is the relationship between critical angle and refractive index concept. If suppose the rarer medium is air or vacuum condition, we take the refractive index of the rarer medium, that is N2, to be 1, and medium's refractive index, we are not sure about what exactly value it has got. So we just consider a standard one, call it as N. Then we have the equation as C sine inverse of 1 by N. That means to say that when the refractive index is larger, critical angle is smaller. So if the critical angle is larger, then the refractive index is said to be smaller. So critical angle as well as the refractive index has got certain inversely proportional relation. So that is all about this topic, that is relationship between critical angle as well as the refractive index. Next, coming on to the applications of total internal reflection. First application, it is brilliance of diamond. That is, due to its too many of the carvings over here which you can see, because of that it undergoes multiple total internal reflection, because of which there is a presence of a dazzling effect. Okay, so here also the refractive index is higher and the critical angle is lower in this case. So that is all about your brilliance of diamond. Next, coming to mirage. You had already studied regarding this mirage in your session 3. That is, due to multiple reflections we get this mirage. Next, coming on to the total internal reflection of the prism as well as optical fibers. These two also comes under the same topic, that is application of total internal reflection. Suppose if they question you, give any 2 or give all 4 applications of total internal reflection, you can just write one is brilliance of diamond, one is mirage, and one is total internal reflection of the prism as well as the optic fibers. So here, reflection of the prism. You know, prism is something which is of this type, triangle shape, 3-sided. So there is a presence of a prism over here which is meant in this way. So you can name this as A, B, C. Suppose if a ray of light is incident on the face AC at an angle called as 45 degree, that is internal reflection will be undeviated this way. Again, it is at a 45 degree, correct? So this kind of prism, that is prism setup, can be used in periscope. It is called as a periscope. Similarly, for the same prism, the incident ray will have a different direction on hitting. So we have that as A, B, C. When this is a case, the incident light which is incident on the face A, B, it comes undeviated at an angle called this as 45 degree. So it moves also undeviated internally, and this is also said to be 45 degree, and finally after hitting here it reflects back like this. So this total internal reflection of a prism, it is used to turn the incident light. We just turn it. So here the incident light is turned to 90 degree. Incoming rays is turned to 90 degree and it is going outwards. Similar way, in the second one, the incoming ray is hitting the face of a prism and again back it is hitting and getting back to itself. So this is nothing but 180 degree. The turning of the incident ray is done for the 180 degree. So this kind of a prism or this kind of second technique, it is used in binoculars. The first technique is used in periscope. The second technique is used in binoculars. Coming to the third technique, that is the incident ray falls onto the AC side of a prism. So suppose if this is a triangle, what you take, that is a prism. This is A, this is B, and this is C. Suppose here there is an incident ray of light which is coming and it pitches onto the surface, that is AC, and it moves away. Again, if suppose there is a light ray, it moves in this way. So if suppose your image is upside down, consider if it is upside down, the ray which is at the head, it comes and reaches the top. The ray which acts as a tail, that is tail part, it reaches over here. So the inverted image will have a correction, okay? The inverted image will be corrected with the help of the third step. So this is how the total internal reflection takes place inside the prism. So it is used in periscope, binoculars, as well as the correction of inverted image. So this is how the application runs, that is application of the total internal reflection actually acts. Coming to the next one, that is optical fibers. You have internally, there is a glass or else a plastic fiber kind of a structure, wherein this part is called as core and the above part can be called as cladding. So how exactly the movement of the light rays takes place? It just pitches within the tube, that is the core side. So this is incident ray, reflects, it finally reaches up at the other end. So this kind of optical fibers can be useful in case of the communication purposes. So this has got, this optical fibers is made up of either a glass or else a plastic. It is the one which has got the core, that is the inside part, and cladding, that is the outside part. And this is the apparatus which is used to transmit the light at the longer distance. Okay, so the core will be having a high refractive index and cladding will be having a low refractive index. So that is all about your optic fibers. This is also one of the applications of the total internal reflection, because series of internal reflection takes place over there. So this is very best suited for the communication purposes as well. And moreover, it is more better than any other ways which is used for the communication purposes, that is the optical fibers. Coming to the next one, that is refraction at the spherical surfaces. So how many spherical surfaces are present over here? We have convex spherical surface as well as concave spherical surface. Convex spherical surface is something which comes out to be in this manner. So it is just the surface what comes to be a spherical. So there is a principal axis which is drawn at the center, and there is aperture, that means the one which is actually necessary for the images to fall on a spherical surface. The part of the sphere which is actually available for the fall of incident light on the surface is said to be aperture. So here there is a presence of aperture, and name this spherical surface as, call it as AB, and this can be called as a pole, and here we have a center of curvature. All these are about the spherical surfaces. Next, coming up to the concave spherical surface, you have the other end of the concave spherical surface. Call this as, it is in this manner. There you have a principal axis and pole, and name it as A and B again, and you have a C point over here. So this is how the spherical surface, that is concave and convex spherical surfaces, are mentioned in case of your syllabus. So now this is refraction at spherical surface, the one which is available for refraction. The superficial area which is available for refraction is said to be aperture. So these are the components of those spherical surface what you are studying now. So what is that pole? So pole lies, if suppose this is a convex spherical surface or this is a concave spherical surface, the aperture is the one which is present over in this section which I am highlighting. So what is pole? Pole is nothing but which lies in the center of that aperture. So, and we have a principal axis over here which passes through the pole. So that is said to be your principal axis. So what is your center of curvature? You have a circle, and the circle's midpoint is said to be the center of curvature. Suppose if this is a circle, and if you want to fill this circle, you can just draw an imaginary line over here. So this is said to be your center of curvature. The point is said to be center of curvature, call it as C. And what is radius of curvature? The distance between this pole. Always we measure the distance from pole to some other object or the image distance. So if you're measuring this radius of curvature, it has to be from this pole to the center of curvature, call this as R, and from pole to center of curvature, call this as R. And next it is radius of curvature, it is done. Coming to the object space. The space exactly, that is the from where the incident ray is emerging, that space is called as object space, and where exactly the refracted ray goes and hits, That space is called as image space. So you have incoming rays are from the object space side and the outgoing rays are towards the image space side. Okay, so that is all about your components of the spherical surface, what you actually have to know. It is aperture, that is the one which is required for the refraction to take place, that is this superficial area, and you have a pole at the center, call it as P, which is named. Center of curvature is at the center, a distance between pole and center of curvature is radius of curvature, call it as R. Principal axis is the axis which passes from the center of curvature as well as the pole, and object space and image space means object space is a space from where exactly the incident light is coming, and image space is a space where exactly the refracted light is passing. Next is Cartesian sign convention. So each and every time, either it might be for a mirror, it might be for a spherical surfaces or else a lens. Each and every time there will be a Cartesian sign which are like a note for us. Understand, it is a note. How exactly the sign convention is taken place over here? That is, all distance are measured from which? From pole to the spherical refracting surface. Remember, always all the distances are measured from the pole to a refracting surface, and then the distance measured in the direction of the incident light is said to be positive. The same thing goes up in the mirror also. Okay, so the distance measured in the opposite to the direction of the incident light is said to be the negative. Towards along the incident light is said to be positive. Against or the opposite to that of the incident light is said to be the negative condition. So this is all about your Cartesian sign convention in case of the spherical surface. So next we are coming to the refraction at a single spherical surface. So there is an equation for it in order to understand the refraction at a single spherical surface. The same equation, not the derivation but the final equation or the expression, we use it in case of the lens maker's formula, which is very important. That is the lens maker formula, which I'll just come up with the next session. Okay, so here I'm talking about a single spherical surface. So I need only single spherical surface. So that single spherical surface, I'll consider it as a convex surface, which is the same for the concave also. So here there is a principal axis. It's like a cloth what you're making a spherical surface where. Okay, so it's like pole has to be there, principal axis has to be there. When you just get ready for a school, what and all things has to be there upon you? It has to be like your uniform, you have to carry your bags, and inside bag there should be your books, box, lunch bag, lunch box, all these things you have to carry. That is the rules what you follow. Similar way, our single spherical cell has also should carry its uniform, right? So what are its uniform? Uniforms are nothing but the pole which is present over here and the principal axis which has got certain center of curvature. Call this center of curvature as C point. Suppose if there is one object which is incident ray falling onto the aperture of the single surface. So call this point as object O, and from the object it is incident on the refracting surface, and this is the normal which is drawn to the surface which passes from this point. Then when it moves from rarer medium to the denser medium, actually ray which is getting refracted, it bends towards the normal. So it is bending towards the normal. So the bending will be in this position. So call here at this position where the two lines intersect, there exactly your image is formed, call it as I. And the point of intersection in this surface is called as A. And for your reference, draw something which is perpendicular and call this as M. The angle which is made in this part, call this as alpha, and the second, that is refraction, is called as angle beta, and the imaginary concepts which is present in this case, it is called as gamma, and this is nothing but the refracted ray normal, and the refracted ray is called as angle of refraction, and the incident ray normal ray together it is called as angle of incident. It is not the inner part, it is the outer part. Normal and the incident ray makes an angle of incident. So this is the picture which we have got. Now from object to the pole, always measure from pole to object. So this distance is called as u. U will be the distance of the object. From pole to the image distance, you call it as v. Small letter v gives the image distance. And from pole to the center of curvature, call that as r, which is called as a radius of curvature. So we have u, r as well as v. And we know that one is rarer medium in this, one is denser medium in this. In this image, the air is denser or the medium will have more density. So that is denser medium means this can be the denser medium. So always the incident is from rarer to denser in this case. So rarer medium has got the refractive index N1 and the denser medium has got refractive index N2. So this is the general thing what we will have to calculate and keep it in our minds. Now consider angle AOM is equal to alpha. Next, angle AIM, call this as beta. Order wise I'll go. Next is angle ACM is angle gamma. We have alpha, beta and gamma angles over here which is present. Now, according to one rule, that is external angle is the sum of opposite angles. So which is the external angle in the first, that is AOM concept. So here AOM in the sense I am considering AO as well as C. In this triangle, which is the exterior angle or the external angle, it is I. So considering only this triangle, you can just sketch it out. The triangle which is present over here, AO as well as C. I am considering this angle, not the one which is present over here. AOC. Okay. It is making an angle alpha and here it is making an angle I and here you have got gamma because this doesn't have any opposite angle but this has, so I am considering the complete thing. So I is equal to external angle is the sum of opposite lying angles. So alpha and gamma. Similar way goes with the second one, that is triangle AC and I. I'm just considering AC and I, ACI, wherein this angle, it makes an angle gamma over here. So here you have R, here you have beta, which is exterior. Gamma is exterior, which is equal to refracted ray plus beta. But you want for refracted ray, so it comes to be gamma minus beta. So you have R is equal to gamma minus beta, I is equal to alpha plus R. So that is the equations. Now, according to the Snell's law, now every time the Snell's law comes into existence, according to Snell's law, I have N1 sin I is equal to N2 sin R. So what is sin I and sin R? Sin I divided by sin R is equal to N2 by N1. But remember students, it is actually a paraxial line is very much nearer. So if the lines are too very nearer, that is the lines which is drawn here are too very near, then it can be told as sin I can be approximated as I and sin R can be approximated as R. So you will have I by R is equal to N2 by N1. N1 goes with I, N2 comes with R, N1 into I is equal to N2 into R. This can be followed directly from this instead of these many steps. Okay, so N1 into I and N2 into R. So we have I and R for which this equation and this equation has to be substituted. So N1 into alpha plus gamma, which is equal to N2 into alpha gamma minus beta. So this is the condition which is present over here. So now we will have to equate those two together. So now on clearing this section, we will have, for the same diagram, the equation turned out to be N1 into alpha plus gamma, which is equal to N2 into gamma minus beta. So this was a set. We know that, as we know, it is alpha is equal to A P instead of M, since this is very much near, I'll be considering AP by OP. It is AP by OP. And we have beta given by, if this is an angle of beta, it is AP by PI. It is AP by PI. And for it is gamma, if that is the case, if the gamma is a condition, then we have AP by PC. AP by PC. Apply these things towards the angle which is given over there. N1 into AP by OP plus N1 into gamma is AP by PC, which is equal to N2 into what is gamma? It is AP by PC minus N2 into it is beta, that is AP by PI. So now here common terms, I can just take AP out and fuse it with N1 by OP plus N1 by PC, which is equal to AP again common out and N2 by PC minus N2 by PI was a condition. AP cancels with AP, so what remains is N1 by OP, N1 by PC. So I can just take, in order, just because your denominator is common and this part, I'll take my this part towards the other side and get my N2 towards the other side. So it becomes N1 by OP plus N2 by PI is equal to N2 minus N1 divided by PC. So what is OP? As we know, OP is nothing but O to P, it is nothing but U, and P to I, it is nothing but V. And P to C, it is said to be R. But somewhere there is something which has to be added. O to P means it is always we are measuring the incident ray from pole towards the incident ray. So it is always this way, that is opposite way. So it is called as a minus U. So I can just replace this equation as N1 divided by minus U plus N2 divided by V, which is equal to, what is N2? It is the refractive index of a denser medium minus refractive index of a rarer medium divided by your PC is R. So this is said to be the set of equation, that is the equation called as refraction at the single spherical surface has got that equation. By using that, we will solve for lens maker formula, which will come in the upcoming session. So this is nothing but the relation between the distance of object and the image distance with respect to the refractive index and the radius of curvature is given in terms of this refraction at single spherical surface. Today's class, we have studied about relation between the critical angle as well as the refractive index and the applications of the total internal reflections, which are those we have studied, and how exactly this prism acts, the total internal reflection the prism takes place, and optical fibers means what. All these things you have studied in today's class, along with about the single spherical surfaces and how exactly the spherical surfaces have got the components and the components distribution. Finally, it was the one what we studied, that is refraction through a single spherical surface, which gave the relationship between the object distance, image distance with respect to the refractive index as well as the radius of curvature. That's all about this session. Let us all meet in the upcoming session of the same chapter. Until then, have a good day. Thank you.